me? Yes, yes, everybody knows.
Everyone knows me. Welcome back. I shouldn't have, but we took lunch too long and then. Yeah. If everyone knows German enough, it's called Viertelnacht.
Viertelnacht?
Viertelnacht. Es geht so. At least one of us understood, so it's good. What should I say? Oh my god. Well, Oli was very demanding, obviously, to me, to give 2 talks. And he said, second, is it better this way? I feel...
No, let's keep it on. I think Lit is better.
This is fine.
Well, Oli was demanding, so he asked me to give 2 talks. And he said, second talk would be more interactive. And I said, at this small scale, it could be more interactive.
The last one was already very interactive, but this is
even more interactive.
I thought since just to use better your visit, I thought it would be more helpful for us to be able to ask you more questions. It's like work in progress and your
well,
work.
No. I became like a Sherlock Holmes if you read Sherlock Holmes well enough. You never tell anything about work in progress. He made a mistake. Well, this is famous anecdote in Sherlock Holmes. He made a quick guess and said everyone in front of everyone that problem is solved this way, blah 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 blah. And but they knew at that point where to go. And they found out what Sherlock Holmes said was totally wrong. So from that time, he never said about work in progress, just keeping his brain, and that's the good idea. So this is work already done and published another paper now, again, Code of Journal this year, and it's done by, recently done by Yano, the master student. She's now, I think, I do a mentor since then. This is why I like it. École Nationale de Pont de Chaussée. I think she's doing PhD right now. And basic idea is to ask a question how convection works in the atmosphere in general. So that's the core part of this talk. And then we talk about trigger of convection. That convection suddenly kicks up. So ask a question, relevance of this question. Intelligence of this concept. And then I made this talk more general because I thought Oli organized a group, or he belongs to climate modeling group. So I thought I had to say something more fit to the climate modeling people. So generally, actually I'm recycling this talk to be honest. That the question of stochasticity in climate modeling. And so time asking question I'm asking is when we can put stochasticity and when we should not. And then confusion here is often we think we need randomness or stochasticity to get probability. And then so bottom line, at this level bottom line of talk is to show we can talk about probability without any randomness in your system. I forgot the title. It's Stern concept of convection. We think we normally need trigger, but point is we don't need trigger. That's point number 1. Point 2 is we can talk about probability without stochasticity. Okay? So, points to make. Atmosphere is noisy and looks like very random. So, this is apparent noisiness and randomness. So it's not real randomness. It's just apparently random. It's not enough to introduce stochastic formulation for a model. And it's a little bit same point, but we should not introduce stochasticity if we can do something equivalent with determinist formulation. Well, something kicks off in pulse way. Let's put pulse stochastic noise without asking physics is not very intuitive thing. And yeah, as I said, we can do a probability without stochasticity. And in a way, this is just an example to make this point, the sudden initiation of convection, what often we say trigger. And we take kind of energy cycle for convection that work by Danvers, Auckland, Sydney. Well, we have 3 papers on this subject, and that's what I'm going to talk about. Oh, this is different format. Oh, because this PDF, you know about it. This sometimes it gives audience the impression that by seeing those things that I don't like stochasticity, but that's not true. That I have a paper on stochastic modeling with Prof. Phillips, and then we apply. Well, in this case, when eyesight collide each other, then you sprinkle the grapple and grapple collide each other. It sprinkles the tiny ice crystals, and that is the ice multiplication process. And then number of ice crystal sprinkle out of collision is not fixed number. Well, you can compute this if your theory is not deterministic, but that's tedious. So it's easier to handle as a stochastic process, and this is and so we plug this system into simple resonance dynamical configuration and use the Fokker-Planck equation for progress. So this is a kind of initial condition for distribution of small ice crystal number and global number. Initially there is almost no global, but then as ice crystal grows, ice gradually grows into global, and then global collide each other to produce the more ice crystals. And then, because this is nonlinear process, we get what's called multiple noise process, multiple noise process. And so if we get more ice crystal, we get more randomness and so on. So we get a finite chance to get more and more ice crystal with time. So this is very stochastic process. Anyway, but we talk about totally deterministic process, but probabilistic today. Any question? Well, this is different. Well, and this appeared in JAS, was it last year? So you can read it and ask, and send me email with all the questions, if you have any. So as a starting point, we try to look at how convection works in atmosphere, in a solid way. And this is a kind of overview. And wisdom is, this is my favorite expression, is stand on the shoulder of giant. Have anyone heard this expression? Yeah, of course Nathan knows this. He is so intelligent that, person who said was actually Isaac Newton. That's very cynical story. But idea is, if you go up, stand at the top of giant, even you are dwarf, you see far, far away. So you follow someone genius already did, and then you can do a little bit better than someone genius did, and that's really progress. If you try to do everything by yourself, you never go that high. Anyway, so in this case, the giant is Arakawa, and this, probably needless is a little bit sick of this Arakawa 74. Keep talking these last 3 days. That in construct this mass-struck parameterization for convection, they construct the energy cycle for convection as well. And we take this over and examine very careful. And this is parameterization context. So you might think this is a little bit conceptual, but I'm going to argue this is very, very solid framework to understand realized convex energy cycle. And I don't know, because this is very inductive and audience hold me. But if everything goes well, this is all I can talk about. either two version, single column version, and then depends, and then I'll explain the Salmon onset convection as well as transformation shallow to deep. That's interesting. And that's basic framework. And we can add kind of spatial dimension. Someone said, I should say, phase space dependence, whatever. It's quasi space. It looks more interesting graphically. Anyway, that's the most ambitious plan. Let's see. Probably we will stop here, I think, from this one experience. But that's the overview. And what does it say? I think something changed. I don't remember what I did. I just put both on here. So this will be an emphasis in the case. So this is a background from convection dynamics point of view. I don't know this Palestine weather well enough. And I understand summer is dry, so this doesn't happen so often. But in European summer, hot day, sunny day, you don't see any cloud at noon, but sometimes cloud develops gradually after 2 p.m., 3 p.m., and you get very, very heavy shower. So this kind of afternoon shower, summertime, is very, very sudden. This is the situation. Well, this out of cloud building, but this could, you get sudden onset convection, and then before about time the sunset dies out and go on. And interesting thing is this kind of lags behind the surface flux forcing. And then it looks very, very sudden and hard to predict. So common notion is there must be a certain trigger mechanism, people say, to induce this process. And so there must be trigger. That's kind of the undebatable hypothesis. And people just ask, what is trigger? And then, because this is hard to predict, looks like something random stochastic. So that's a common wisdom. And point to make in this talk is we just have to involve the nonlinear process for generating convective kinetic energy by buoyancy. So that's a basic point here. B is buoyancy, assuming everyone knows what buoyancy is, and this W is vertical velocity. And the way to see this is with this rate of generation kinetic energy, we assume to be equal to work done by buoyancy. This is what we see by textbook. You got buoyancy and lift this parcel by distance dz, then we get this amount of work. And in my personal data, many people don't realize this is not good expression. I think I got, that this is Lagrangian, and your model, in most of the time, 99% time, is Eulerian. So this distribution is not consistent. We have to replace the dz by rate of change and using vertical velocity. If you get vertical velocity, W for the value. dz is replaced by vertical velocity by W multiplied by small increment of time. So rate of generation kinetic energy by buoyancy becomes buoyancy multiplied by vertical velocity with small increment of time gives you generation kinetic energy over this time. So key thing is this is nonlinear, buoyancy, vertical velocity. And our key argument is this nonlinear. We just have to take care of this nonlinearity explicitly and recover this Sagan offset. And we don't need anything else.
So buoyancy is not constant?
No, we predict the buoyancy. We predict buoyancy with time in a certain way.
Okay, so buoyancy depends on Z and therefore the time?
Well, you have a buoyancy equation, right? Well, you have equation of seed and moist mixing ratio and combining them together, you can write down the buoyancy equation. Well, that's part I don't do carefully. So you have a local rate of generation buoyancy based on everything. And then we integrate vertically that I'm going to do, and get something conceptually reasonable. So that's the outline. So, but key point is, yes? Yeah, no, someone said something, I think.
Yeah, I think that.
Yeah.
I'm sorry.
Was it a mistake?
No, just when you get it from the equation of state, it's not the buoyancy.
No, equation of state give a buoyancy, but the tendency for state variable must be computed prognostically. So make a long story, you can write down prognostic equation, buoyancy, combine them together. Yeah, you didn't, okay. You understood this or you didn't ask a question, in fact. So just repeat this point. And, now I'm trying to kind of close the problem. This is, I moved to big parameterization context. We can forget about it, but this kind of framework I take. Anyway, let's show what this says. This is the generation rate of kinetic energy. And the idea is to integrate this quantity vertically, but do this in kind of context of convection parameterization. So key thing is you multiply by fractional area occupied by convection. This is not crucial part. We can do it without it. And multiply density because to get get a unit of joule rather than metabolic second square. And so we multiply sigma intensity here and integrate vertically from bottom to top, whatever you're interested. And one trick is into this kind of, this is a key thing, defines spatial variable. We imagine somehow vertical structure of this vertical motion is fixed for convection. And there's certain amplitude that we have to worry. By doing this, then we take out this time dependence of convective amplitude. And what all left is expressed as A. And if you follow this O algebra, you can see this A is defined by vertical integral of this vertical profile or vertical velocity or mass flux multiplied by buoyancy. Again, and then so kind of tricky, this is supposed to be normalization quantity, and nonlinearity of the program is attributed to this part of amplitude of convective momentum. So we make this translation. So rate of the current energy is controlled by generation by buoyancy and certain dissipation by generation is given this way. And this is drastic simplification, but I hope everyone swallows that we just assume Rayleigh damping with constant time. That we estimated by certain crowd estimations, 1,000 milliseconds. Well, if you don't trust it, you can put any number you trust better, but that we do here. So that's an equation of kind of energy. And to close this, main thing worries us is this quantity. Oh, did I give a name? I forgot to say. Yeah.
This Rayleigh damping is very problematic, especially in convective conditions. I mean, what is the justification for Rayleigh damping?
This is not Rayleigh damping in any physical sense. It's actually crude expression of what pressure is doing against convection. And this is a paper to read. I wrote a paper, 2014, DAO, Dynamics of the Ocean. Well, she didn't agree to be a co-author, but Kathy Horneger provided me crowd result model simulation result and some analysis. And look at how this dissipation can work. We need careful energy integral. And well, I said dissipation, but this includes everything other than buoyancy generation rate.
Sort of relaxation? Or what is it?
No. Key term for this is, and one thing you have to realize, convection is open system. It's not, so something more than forcing and dissipation going on. So there are entrainment and detrainment air. So detrainment contributes to the dissipation. That's other thing. Of course, there are real dissipation and then this detriment processes. And number 3 is pressure forcing from bottom to enhance convection, and then this pressure depressing, so to say, from top, and that changes the total kind of energy. That works kind of extra dissipation term. Actually, I call it dissipation, but it could be extra energy generation term. But as it turned out, this pressure forcing actually works other way around against buoyancy. And that works as a major contribution for this damping term. And you can see my paper that we did scatter plot, where I did scatter plot for kinetic energy against the total dissipation rate, where you get crowd going up with about 1,000.
So tau, the time scale here is a sort of residence time inside
Of air parcel, if you like. Yeah, that's just describe the pressure response time scale. So I call it Rayleigh damping, mathematical Rayleigh damping. Mathematician would agree with me this Rayleigh damping, but this is not physical Rayleigh damping, of course. And then, this is called crowd work function, this A, and roughly equivalent to, I forgot to say what we call cape. Our own proposal called it potential energy convertibility, because this convert potential energy to kinetic energy, and it measures capacity. So short name is back. And always every talk we have to decide how to call it. So I will stick to this name, POC, PEC, or it's not true, but I just call it potential energy, because it's not really potential energy, but it plays a role almost like potential energy in this whole system. So that's energy and kinetic energy. So we need equation for this PEC or potential energy, and this is on algebra. We have to look at appendix 3 of Alka-Schubert, but conceptually, if as convection develops, the system consumes this potential energy, so you get a kind of Rayleigh damping, this constant, and there are certain processes to change this potential energy by large-scale processes. So that SNL system, as derived by Alka-Schubert, in fact, and this is very nice closed framework, and it's given in translation context, but I hope you understand that it's regardless we translate convection or not, this is basic energy cycle for atmospheric convection, at least in conceptual way. You can try to provide different variation for this formulation, but whatever you do, you will provide roughly end up with this framework. So this is pretty nice, except for problem is we got 3 variables: kinetic energy, and this potential energy, and convection amplitude interval. Convection protocol momentum. So we need 2 equations with 3 variables. So we need certain conditions to close. And what we decided to do was assume this kinetic energy proportional to vertical convective momentum with certain constant. And you may think this is a bit strong assumption, but if you, the thing we did was assume kinetic energy proportional to certain power is vertical momentum, and then write down the general equilibrium solution for this solution, and compare with some of the crowd distribution results, and make a story short, this linear assumption is most constants. So that we assume. Let's skip those. So this is a set of equations, energy equation for kinetic energy, potential energy, and the way to relate kinetic energy to vertical momentum. And we do the only academic side. This is nonlinear. This is generation that is nonlinear. And we don't dimensionalize this. That's kind of handy. Can we get this kinetic energy, kinetic value, and the equivalent for potential energy? We shift this family way. This is stable. So we do differently. Kinetic energy, zero kinetic energy, zero with non-gradation. But the potential energy zero up to non-gradation is equivalent value. It's a bit confusing, but I thought this looks nicest this way. And F tilde is certain, yeah, detail. Anyway, so this is easier to read. I don't know. Either we stick to this or this. But point is, we get this nonlinearity x.
But you get a second order set.
Second order?
Second order, yeah. This type of equation is actually second order. Two dimension.
Yeah, two dimension, yeah.
Two dimension.
Yeah, exactly.
No chaos.
Huh?
No chaos.
No chaos. Yeah, well, this is not first time I got this question. Well, it's nothing chaotic, that's key. It's not stochastic, no chaos, but I believe so useful to seek in terms of probability. That's the point we are getting. Anyway, I don't get what we do next. Oh, can we memorize this? So this is handy, right? So this must be blank now. So we write x-axis here and y-axis and see how it goes. The problem is this formulation is what? Yeah, maybe. Problem is we forget one is here, so it's fine. So this one is large-scale forcing. So, well, I think we'll draw x here and y here. Imagine we start from very, very small kinetic energy potential. And we get, oh, I didn't explain, we are still constant large-scale forcing. So this is very small, and this is small, small. And start from very small x and y kinetic energy potentiality. And we get constant forcing potentiality y. So what happened is,
You have a fixed point at 0, 1.
huh?
You have a
Fixed point
0,
is, I think,
1, 0.
1, 0, 1, 0. So x, y, this is 0, 0. Well, this is minus impact. So equivalent value y 0 and x 1. Equivalent solution here. So we put very negative y, no, very small y. I'm contrasting here, I think. Never mind, small x and small y. No, x is small, that's important. Then y doesn't matter too much, I think. You put very negative y and start from here. But anyway, since x is small, nothing happens initially. We neglect all those. Starting from here, this term is only denominator. So what happened is potentially just increasing with time. But because x is small, nothing happens. Until this y is large enough and positive, then this term suddenly plays a role and kicks on the convection. We feel not extra enough to get convection. Once convection kicks on, that confuse constant potentiality. And once it begins to constant potentiality, you get loose dimension with the convection. So it goes down. So system goes like this kind of triangle type. Recovering of potentiality, and this to the potentiality, just make convection like that. And if you don't trust me, so this is a degree of dot for volume syndrome. This is the equivalent solution. I also get this kind of solution. If it's closer to the equivalent solution, it's circular. But we get sudden onset and you get convection.
Is this different from the site where Carol built, or is this?
That should be this one.
They
They got this equation, but they didn't solve anything. So neither is into the bottom line. What we call quasi equilibrium just say this balance is zero. And the basic thing they said was let's assume this to get convective mass flux. So
It seems from your plot that you're conserving some sort of energy.
this system is somewhat intelligent and Hamiltonian. Yeah. So, well, one group of people I should credit is Penn and Randolph. They look at this equation about beginning of 90s, a class paper, somewhere in 98, never mind. They assume time energy proportional square of transfers. And that is very boring system. That is more intuitive because it's square vertical velocity and this is linear vertical velocity. So that's most people think. Then if you do the algebra of this reduction, this term becoming linear, this x drops out neighborhoods. So it becomes just simple linear system and getting more here having this linearity. So that is the building part. As I said, this is standing on short of giants, so there is no magnetic originality. Just add something in there, that's interesting. So that's what we got. Now look at time series. Same thing. I think the time series of what this is. Yeah, time series of convex kind of you see as someone said. And I think we repeat it for 4 cycles. This cycle number 1, cycle 2, and this cycle number 4. And the second curve, it just shows starting with slightly smaller potential energy. I forgot the number factor. So then you get a little bit of delay in initial phase, second phase you get this much. And as time goes, you get more and more discrepancy for concept of convection, and what you may argue as maximum as well. So all those systems completed the mistake.
Slightly different point.
Starting,
First place.
yeah,
So with
slightly,
time,
yeah.
the difference between.
No, this is nothing miracle. Just a little bit unintuitive, that's all. I'm not saying anything great. We just standard difference keep the uncertainty for concept. I don't say anything particularly surprising, except for if you are obsessed with the idea of stochastic trigger, it must be surprising. If you're not, it's just something obvious. So depends on where you are. If you don't even notice this stochastic trigger, it's obvious as I think. But I have to show this for people insist on stochastic trigger to say we can get standard onset, predicted onset without any trigger, even without any chaoticness. System is totally, I forgot to say this. Yeah, this is system perfectly periodic.
Yeah, it's periodic.
Yeah, but we still get uncertainty on onset of convection. And main thing I didn't say was this period is getting longer and longer, farther away from the given solution. So it goes, things going around in different periods. That is the shift of onset. So there's nothing surprise, but it's kind of surprise if you always think, oh, trigger, and stochasticity. And I'm just saying.
But trigger is just like one branch on this phase-space trajectory.
Okay, well, yeah, I don't know. It's actually, I said trigger.
The onset of, let me ask you, the onset of convection is when you change, what is it, can you put the phase-space back?
Yeah.
When you change y, y is your convection?
Yeah.
Okay, so it's the bottom part.
No, X is convection part. X is convection, yeah. Y is potential.
Y is what?
Potential.
Not convection.
So you get feature the potential energy and discharge potential energy is convective activity and convection life.
The thing is, it goes this way, upward, probably fast.
Yeah, it's
very fast.
Are you familiar with elliptic function, sir? This solution is elliptic function. We didn't look at it. So if you know elliptic function well enough, you can answer this
If you
question.
have an atomic, you can check the rate of change with time. If you have the exact moment. matters that much.
Gee.
It's a nice exercise, but
Well,
you won't tell much more than what you thought of numerically.
no, we can estimate this. This older one.
Yeah, when
No,
x
I-
is 0, y dot is largest. When x is close to 0, then y dot is largest.
Yeah. Yeah, okay, you're right. It goes very fast first and then becomes slower. Yeah. That's what I agree. So anyway, we got kind of uncertainty due to the uncertain initial condition. I put this. Oh no, I made a mistake. So we get uncertainty, so we want to predict about uncertainty or probability for onset of convection and so on. So we need a framework for predicting a probability. The way to go is to use what's called Liouville equation. And now I always say this, probably if you studied physics more or less, you heard about Liouville equation. That's a part of standard curriculum of statistical mechanics. And the trouble is we get the impression that this is only for statistical mechanics, but it works for any dynamical system. Right dynamical system this way. In our case, it's because x and y in certain rate, right hand side, we can write symbolically x dot bold and f bold, and that's general. And basically, the Liouville equation is probability is kind of conserved quantity by following the evolution system. So it's basically the same thing as conservation of mass density. Imagine you got a flux of probability by forcing this side, and then other flux of probability density by forcing F. Then so this differential of this tendency is the rate of change of probability for this box. So make a long story short, you get a divergence of probability for forcing vector define the rate of change of probability density. So that's what Liouville equation is. Yeah, well.
You could make it more complicated.
How come?
Take Fokker-Planck equation.
No, point. This is deterministic, so that's a beauty. So with using this equation, we can compute the probability density of this system. This is nothing special, but just showing we can compute it. So this is hard to see, right? Initial condition is here. There must be dot. I don't see it more. Oh, no, it's somewhere around here. Anyway, can you see this dot? So this is after don't do time 1, and then we start see stretching of structure. So as convection initiates, we get more uncertainty in probability distribution, and get long tail here as getting to decaying phase. And interesting thing is it's getting back here. You can see this, right? And important thing, you probably don't see this anymore. The point is, you get that kind of oscillation of probability density. You get very uncertain state as active convective phase, and then you get the least uncertain phase in inactive period. And this situation kind of repeats, but in kind of more interesting way. This is the same thing. This right part is kind of continuous. This is, I think this is the second cycle. I can't remember. So a cycle repeats this act, this onset period, active period, gives you more and more steps of probability. And this follows this streamer of this system of trajectory of the system. So we see more and more uncertainty for onset of convection in this way. So this is a kind of club into simple framework. Well, this is kind of discontinuous and it's tedious to see. So we decide to see a chance of having active convection. Active convection with xc is equal to 1. That's the equilibrium solution. And to see, so we can give a chance for having an active convection rather than Xe rather than X rather than 1. And that is solid curve here. So this initial first cycle, convection most likely onset sometime after 2, and then you get convection always and convection died out. And this is second, fourth, I think this must be 8th cycle. And as cycle repeats, sometimes you never get convection. And the chance of getting convection is kind of much earlier. So you get the dispersion or diffusion of probability. And something we got here is probability of finding a growing convection. So I forgot that condition, but we can distinguish this probability either y, well, x is increasing or x is decreasing. So there's a chance for having an increasing convection. This is a chance for having a decreasing convection, and we see this. These two curves also discloses the standard. So it's kind of simple quantification that we can see an uncertainty in objective manner in this simple
In
system.
other words, you can be on the right of the fixed point, either for positive or negative y.
Would you say that again?
What these two graphs mean is there can be to the right of your fixed point, but either positive or negative y's.
Yeah, you can see. Well, yeah, okay. So you can do this perturbation problem for this.
These two graphs are positive and negative.
Yeah, I think you can. Yeah,
Negative, right?
yeah. I think you can get analytical expression for this situation in that way. Yeah, that was.
Sorry, I think I lost you. What do you mean by first, second, and fourth cycles if it is periodic?
No, system periodic, but you get two different periodicity. So distribution disperses more and more with both.
Use the initial condition.
Yeah. So I'm looking at this thing roughly correspond to period of this solid curve. So this period is roughly 8 for this solid curve system, but this is slightly longer than 8.
Okay.
So it keeps shifting. And this is kind of visualization in two-dimensional space. So we see an increase of uncertainty, and just we plot same thing as a unit, as a probability.
So your initial condition actually was a discrete set of points.
Mm-hmm. Yeah.
A block.
So, yeah, and well, so far kind of straight. But something we are really interested is not a given point convection is active or not, but it's other way around. We want to know when convection starts. So, can we predict this? And this is kind of fun part because we got this probability. With given time, we can compute probability of certain event. In this case, last plot was chance of having x larger than certain threshold. But if you use this part called Bayes' theorem, we can twist it. So the use event as a condition, and at what time we will get this event. That is essentially probability for finding a timing of onset of convection. And this is essentially what Bayes' theory says. We just have to multiply by this factor in this. Assuming not even familiar with this Bayes' theorem, the derivation is done simple. This is a joint probability for event and time, and we can write in two different ways. So we get whatever condition you get event, and you have to multiply for having, well, probability finding this particular time, that gives joint probability. The other way around, you find probability for event and condition event. You have to get the multiplier condition for the probability of time. So combining these two expressions give you this theory. Well, I always feel trouble with understanding this intuitively, and I don't know how to interpret this. But if you do oscillation process, it's kind of Kalman filter, but kind of. It's not same thing. It's conceptual. So we're, yeah.
I'm not sure I understand the left-hand side of this equation. The P of epsilon t. Not this one. If you delete it, then I understand the rest.
If
you delete it, then the rest I understand.
Oh, interesting.
Right. Yeah,
This
I
is,
understand.
but not this one.
Right. What does it mean?
Well, joint provider having a certain event and having a certain time. Well, this is funny. I don't know how to say this any better. It's better than just finding a particular time. No, it's just T is something special. So you just have to, this is chance for having an event A and B. Then we can write this chance for having an A and B in two different ways. So time is kind of awkward, but we can use time as an event conceptually. That's what I'm doing here. Yeah. So event here is having the onset, we assume moment that X time energy crosses certain threshold XC, which is actually 1, with increasing tendency. So that is event. And this is debatable, kind of philosophical. We can derive this only philosophical way, I am afraid. That having finding a particular time t over analysis period large T is 1 over T, because, well, just pinpoint your time on watch, and if you do it in totally random way, you find every time with equal chance. That's what it means. So if you solve these two conditions, you can compute the chance for finding an onset of convection at certain time. Are you happy? I forgot the last expression. But what turns out is this normalization kind of trivial. It's same expression. I have to do this if it's necessary. It's same expression, and you don't have to worry about this in the end, because this is just integral for all events. So it's kind of constant. And make a long story short, you just have to normalize this. This must be equal 1 from for all possible xc. So if you integrate from 0 to infinity, this must be 1. In this case, we do this for final period from 0 to t. So that must be 1. So that's only difference, and you get kind of constant multiplication. You just normalize this probability as a function. Probability event gives you probability for time. So that's what happens after some algebra. I didn't prepare the final expression. So we can do it, and this is kind of demonstration for having a chance for C of onset convection and the termination convection. So this is cycle 1, and then 2, and 4, and 8. Well, I guess point is really showing that we can do it and show that this probability distribution disperses with time. Something we did here was, this is not fascinating, slightly different initial condition. That much smaller initial potential energy, and see where we get delay of onset, most likely onset. And then, but we need a kind of qualitatively different result, or qualitatively same result in this case. It's something interesting, but it's detailed. Go ahead.
How should I interpret the fact that it peaks only for the first cycle, and then it dies out in time?
Well, we just replotting this.
No, but I'm saying physically, what does it mean? It means that for a given system, it
You're just adding the
when
uncertainties.
No, I'm not adding.
when I
Well,
initiate.
it's only initial condition uncertainty gives the,
That accumulates.
yes, the cumulative
I'm saying
cycle.
for the first time that
Yeah.
convection is sort of triggered.
Well, so this, well, in a way, there's nothing profound here. What happened? Where was it? Yeah. This onset time spread with time, right? In this simple time, 2 time series plot. And I'm just quantifying this spread over time. So there's nothing profound. And then only point is show we can do this.
I think the point is that if you look at the Liouville equation,
Yeah.
the velocity term,
Well, you call this velocity?
yeah, the F, yeah, the divergence of F is not zero.
Exactly.
And I think this is what makes the whole...
Yes, exactly. That's very, very good point.
The
So,
divergence of F is zero, you can just pull it out of the,
No,
you can pull it out of the,
no, you cannot
if
pull
you
it.
can
Depends.
pull, if it's constant, if
It's
the
not
divergence.
it's not constant. This the velocity.
It's not constant.
נכון, זה הקונסטנטה, זה משמע קונסרבטיבית.
No. If you take x derivative here, you get y. Y derivative, this is 0. So, total divergence velocity is y. And that's exactly the point, I think. So, yeah, well, this keeps very. I don't have very, very deep knowledge of dynamical system. So, if I know dynamical system better, this talk will be much more interesting, I'm afraid. But yeah, I'm missing very interesting aspect to point out. But I think this is one point that, yeah, as you said, velocity is non-divergent in this system, and that makes system interesting, and so on. Anyway, I'm just showing we can do those things, because system is very simple, and then so this is the main part. I think this is exactly one.
Yeah, I think this is.
Yeah, well, this is conclusion, and I say discussion. I can add few other things, but kind of wrapping up. So in sudden initiation convection is explained by nonlinear buoyancy, buoyancy generation process of kind of energy. So we can introduce anything trigger in a particular sense, or trigger. This is kind of confusing notion, but triggers suggest something special at the top of normal physics. In that sense, trigger doesn't exist, and neither stochasticity, and that we can do the probability prediction into a Brouwer equation, thanks to simplicity simplicity of system, and timing probability. This is one part. Into this Bayes theorem, we translate time evolution probability to timing probability. I found this is fun to realize. Well, this bit song process, people try to add something trigger to understand trigger, but well, there must be trigger or something, whatever, I don't mind. That there must be a trigger, but there may be a trigger, but trigger doesn't point to anything. So we have to say, if you're interested in trigger, you have to say what process actually you're talking about. So we say there was a trigger. Oh, so that's why convection started. That doesn't explain anything. So even though this conclusion is not generic, and then something special going on, but we should not call whatever special as trigger. We have to pinpoint what this something special is, if there is anything something special. Yeah, well, we can think space dependence and so on, but I think I stop here and I get more questions.
You didn't answer the basic question.
What
Why
I missed the
is there
same?
more probability to have rain in the afternoon? Always in the afternoon.
Well, no, it's not perfect answer.
No, it's not.
Well, this is a qualitative answer from from the morning you get heating of the surface, accumulation of potential energy. So from morning to evening, you keep increasing potential energy. And then stops and then coming down if convection doesn't keep on. The point is, system is not spontaneous to increase potential. You have to wait long enough. So noon time you get highest heating. So I think we have to change this to periodic forcing to make this point explicit. So that's simplification. So noon time you get largest forcing. But we have to wait a little bit more to see any initial conversion. That is sometime afternoon. And so this is not well done yet, but give you answer at very, very conceptual level. And yeah, I sort of doing a periodic forcing. This is mathematically not interesting. It's not, we can't solve it analytically. Well, we can run it numerically and see, but that is not meine Geschwindigkeit, not my taste. So, and everyone can do it. So, please try and convince yourself.
Nice. Thank you so much. This is we sort of out of time. Thank you so much for
Yeah, thanks a lot.
taking 2 seminars in one day with a long lunch and 2 glasses of wine. And,
Well, I missed third, by the way. I missed the third glass.
you missed it. Oh,
No, sorry, I'm joking.
yes, you should have gone for the bottle.
No, shall we have another glass of wine? Okay, thanks.